Welcome to the video for section 6.5, Solving Equations Containing Rational Expressions, for Math 90. Our goal in this section is just to learn to solve equations that contain rational expressions. Back when we were adding and subtracting rational expressions, you may have been wondering why we couldn't just clear the fractions on those darn things and make them easier. Well, unfortunately, we can only clear fractions if we have an equation, not if we have expressions. That's because in order to clear fractions, we need to multiply both sides of an equation by the least common denominator. That's what keeps the equation balanced, that we've done the same thing to the left side and to the right side. When we're working with expressions, there's no left and right side because there's no equal sign, and so we can't do the same thing to both sides of the equation. The good news is that in this section, we are going to be working with equations, so we'll be able to clear the fractions and then solve what we get so that we end up with an answer to the problem. To get us started, we're going to look at solving this equation by first building up each fraction so that it has the same denominator, and then clearing the fractions. The first thing to do then is to figure out what the least common denominator is. I have a 6, a 2, and a 3. And so, sort of by inspection, I can figure out that the least common denominator here is going to be 6, because that's a number that all three of those numbers will go into. Now I'm going to work on building each of these up to have a denominator of 6. 5x over 6 already has a denominator of 6, so it's set. Now 1/2 and x over 3 don't, so I'm going to need to build them up. Off to the side, I'm going to do a little bit of scratch work. I have a 1/2 here, and I want to do something to it to get it to be a 6 on the bottom. What do I need to multiply 2 by to get it to be 6? The answer is 3, but whatever I do to the bottom of a fraction, I need to do the same thing to the top to keep things balanced. When I multiply across now, I get 3 over 6. 1/2 is the same as 3 over 6. So back here in my equation, I can replace that 1/2 with a 3 over 6. And then with the x over 3, we're going to go through a similar process. We're trying to get our goal denominator of 6. And in order to do that, I need to multiply top and bottom by 2, which gives me 2x over 6. Back here in my equation, I replace the x over 3 with 2x over 6. Notice that at this point, I could reduce the 3 over 6 to get 1/2, or the 2x over 6 to get back to x over 3, but that would undo the hard work that I've done. I was deliberately unsimplifying these fractions to get a common denominator. Now that everybody has the same denominator of 6, if I multiply both sides of my equation by 6, and think about distributing so that every single term gets multiplied by 6, we'll see that the 6's all cancel, and I'm left with this nice equation that doesn't have any fractions anymore. Now it's 5x plus 3 equals 2x. That looks a lot better, doesn't it? Now I can finish solving this equation. Say I'll go ahead and move the 5x over to the other side, subtracting 5x from both sides, to give me 3 equals negative 3x, and then I'll divide both sides by negative 3, which gives me x equals negative 1. Once I cleared the fractions, things got a lot easier. Now, building up our fractions so that they all have the same denominator isn't the only way to clear the fractions. You can also just start by multiplying through by the least common denominator. So here's that same problem again. Again, we notice that the least common denominator is 6. This time, instead of building up each fraction to have a 6 in the denominator, I'm going to start by multiplying every single term by a 6. That is, I'm multiplying each side of the equation by 6, and then simplifying and distributing. So when I multiply each side by 6 and then distribute, I can now cancel out the 6's here. Here, 2 goes into 6 3 times, and 3 goes into 6 2 times. All of my denominators have canceled, and when I rewrite this, I've got 5x plus 3 equals 2 times x. This is back to that same equation that I had on the previous slide. And if we solve it, we'll get the same thing. X equals negative 1. The point of this little exercise was to show you that there are at least 2 ways to think about clearing the fraction. In the first method, we started by building everything up so that it had the same denominator. And then when we multiplied through by that denominator, everything canceled in the same way, so we were left with just the numerators and an equation. In this example, the second time, we went straight to multiplying through by the least common denominator, and then we had to be a little bit more careful about the way that the fractions canceled. For instance, here, we had a times 6 and a 6 in the denominator, which canceled out to leave just 1 behind. But here, when we had a 6 and a 2, they canceled, leaving a 3 behind, and here, a 6 and a 3 canceled, leaving a 2 behind. So we had to be a little bit more careful and pay attention to what was left behind after we canceled the fractions. Now we're going to look at some equations where the stuff in the denominator isn't just a number. However, solving these equations with rational expressions will follow just the same idea of the two examples we just looked at. I'm going to start by building up each expression to have a common denominator, and then clear the fractions. That'll leave us with a much nicer equation to solve. Here I have 3 over x minus 1 equals 6 over x plus 4. My first step is to figure out what my least common denominator is. Both of my denominators are already factors, so this is actually pretty easy. My least common denominator will be x minus 1 from the first denominator, and x plus 4 to keep the second denominator covered. Now I'll do a little bit of scratch work off to the side to build up each of these two fractions to having the same denominator. I start with my 3 over x minus 1. My goal denominator is x minus 1 times x plus 4. At the moment, I'm only missing the x plus 4 piece. So I multiply the bottom by x plus 4. But whatever you do to the bottom of a fraction, you've got to do to the top as well. When I multiply this across, I get 3 times x plus 4. Then I'll do the same thing over here for my other fraction, 6 over x plus 4. My goal denominator is x minus 1, x plus 4. In order to fix this to have the x minus 1 and the x plus 4, I need to multiply by x minus 1, both top and bottom. Multiply across, and I've got 6 times x minus 1. I take my spiffy new built-up fractions back over to the equation. Remember, this 3 over x minus 1 is the same as 3 times x plus 4 over x minus 1, x plus 4. And that equals 6 times x minus 1 over x minus 1 times x plus 4. Now comes the big moment where I can multiply through by the least common denominator to clear the fractions. Notice that both of these have the least common denominator. So when I multiply everything by x minus 1, x plus 4, all the denominators will cancel. Here the x minus 1 cancels, the x plus 4 cancels. The x minus 1 cancels, the x plus 4 cancels. If you wanted to, you could probably go straight to just writing down 3 times x plus 4 equals 6 times x minus 1. This equation should look a lot nicer than the one that we started with. If somebody handed you this, you would know exactly what to do. You'll start by distributing, making this 3x plus 12 equals 6x minus 6. Then we'll start getting the x's on one side and the numbers on the other. I'm going to subtract 6x from both sides, and also I'm going to subtract 12 from both sides. That leaves me with negative 3x equals negative 18. Now I can go ahead and divide both sides by negative 3, which will leave me with x equals positive 6. If we wanted to, we could even plug our number back into the original equation to see that it works. We'll go ahead and do that check. So I plug my 6 in back where the x was in the original equation. Over here, I get 3 over 5 equals 6 over 10. And sure enough, that's true, since the fraction 6 over 10 reduces to 3 over 5. So it looks like we have a good answer. Now I'm going to go ahead and show you that same example again, but this time without first building up a common denominator. I still need to know what my common denominator is, though. My least common denominator is still x minus 1 times x plus 4. Now I'll multiply each side of my equation by that least common denominator. I sometimes like to write this out with a little bit more space for myself. And then I write down my least common denominator that I'm going to be multiplying everything by. Notice that on my left side, the x minus 1's cancel, and on my right side, the x plus 4's cancel. Now I'm left with 3 times x plus 4 equals 6 times x minus 1. Notice that this is the same equation that we ended up with last time, and if we went through the steps of solving it, we would still get x equals 6. Both of these methods are perfectly good for clearing the fraction. In this first method, we're using some skills that you just recently learned. That is, how to take a fraction and build it up to have a new denominator. Some of you may find that you really like that connection back to adding and subtracting rational expressions. However, some of you might find that you really prefer this method where you multiply through by the least common denominator and then have to pay attention to what cancels and what didn't. Whichever method works the best for you is the one that you should use. So go ahead and maybe practice using both of them and then decide which one you like and go ahead and stick with it. Throughout this video, I'll try to mix things up so that you can see examples using both methods. For my next example though, we've already got a common denominator, which is great. Here I have x plus 5 over x plus 3 equals 2 over x plus 3, and I want to solve and check my answer. Now, because these two have the same denominator already, I can sort of just ignore the denominator and write down x plus 5 equals 2. Or I could think about multiplying both sides by x plus 3 and noticing that it cancels out. Either way, I'm left with this nice little equation, x plus 5 equals 2. So I'll go ahead and subtract 5 from both sides, which gets me my answer, x equals -3. That's all well and good, but we're supposed to check our answer. So let's go ahead and plug -3 back into the original equation. -3 plus 5 over -3 plus 3 equals 2 over -3 plus 3. Now, my top looks pretty good so far. -3 plus 5 is 2, but -3 plus 3 is 0. Division by 0 is a problem. Remember? This makes the math world explode. See? I told you. There it is. It's exploding in fire. The point is that even though we didn't do anything wrong in our process of solving this equation, we still ended up with a solution that doesn't work back in the original equation. Because when you plug it in, you get 0 in the denominator, which is always bad. So our final answer here is actually going to be no solution. There is no number that will make that equation true, at least not without trying to divide by 0. With that in mind, let's go back and review the idea of the domain of rational functions. Remember, with rational functions, a lot of times we have some restricted values because we don't want to divide by 0. That is, we have some values that x is not allowed to be. For example, let's take a quick look at this equation and decide what numbers x is not allowed to be. When it comes down to it, what we don't want is for the denominators to be 0. So x minus 7 is not allowed to be 0, and x plus 3 is not allowed to be 0, and 3x minus 4 is not allowed to be 0. This little equation tells me that x is not allowed to be 7. This one tells me that x is not allowed to be -3, and when I finish solving this one, it tells me that x is not allowed to be 4/3. As we just saw, a potential pitfall of solving rational equations is that you can end up with extraneous solutions. Basically, in the process of solving the equation, you might, through no fault of your own, end up with a solution that doesn't actually work back in the original equation. That makes it really important to check your answers. You can also do a sort of a pre-check on your answers by checking the domain of the original equation and then making sure that none of your answers are outside the domain. So our steps for solving an equation with rational expressions is this. First, factor the denominators and find the least common denominator. Then clear the fractions using whichever method you like. Solve the equation that you get, and then make sure to check all of your solutions back in the original equation. Toss any extraneous solutions. It must be time for some worked examples. Here's my first one. We're going to solve this equation and then check our answers. Now, before I even get started on this one, I'm just going to make a note to myself off in the corner about what the values are that x is not allowed to be. When I look at this, I notice that x can't be 0, otherwise I'd be dividing by 0. And I also notice that x can't be -1, again, otherwise I'd be dividing by 0. So if in the process of solving this equation, I end up with x equals 0 or x equals -1, I know that those won't really be part of my answer. Now that we've done that, let's get down to following our steps. Our first step is to figure out what the least common denominator is. Conveniently for us, all of these denominators are already as factored as they can be. So I can just write down what my least common denominator is. I notice that I need an x to cover this guy. I need an x plus 1 to cover my second fraction, and I also need a 56 to cover my third fraction. I'm going to go ahead and write this down as 56x times x plus 1, just because I like having the number out in front. It's really just a personal preference. Step 2 is to clear the fractions. I'm going to do that by immediately multiplying everything by 56x times x plus 1. When I do this, I like to write things down and give myself a lot of space. I have 1 over x and 1 over x plus 1, the minus sign in between them, and that equals 1 over 56. Now I multiply every single term by 56x times x plus 1. 56x times x plus 1. 56x times x plus 1. I didn't really give myself enough room there. And then I've got 56x times x plus 1. You can also think of this as all being over 1 if it helps you keep your numerators and denominators straight. In my first expression over here, the x cancels, and I'm left with 56 multiplied by x plus 1. My second one, don't forget that I've got some subtraction here. The x plus 1 cancels, and I'm left with 56x. In my third expression, the 56 cancels, but nothing else does, so I'm left with x times x plus 1. Now that we've done all that business of clearing the fractions, we're down to a nice equation that you know how to solve. When you look at this equation on its own, 56 times x plus 1 minus 56x equals x times x plus 1, what's the first thing that you want to do? Hopefully you're thinking distribute. That's the first thing I'm going to do here. I'm going to write this as 56x plus 56 minus 56x equals x squared plus x. Now I'm going to combine like terms, since I see that on the left-hand side I've got some nice things happening. 56x minus 56x is no x's, so now I have 56 equals x squared plus x. Before you try to do anything else, take a minute to step back and look at this equation. 56 equals x squared plus x. That's a quadratic equation. You know how to solve this kind of equation. The first thing that you need to do, though, is get it set equal to 0 and then factor. So I'm going to start by subtracting 56 from both sides so that I have x squared plus x minus 56 equals 0. The next step in solving a quadratic equation is to factor. X squared plus x minus 56 factors as x plus 8, x minus 7. Now I have two things being multiplied together to equal 0, which tells me that either x plus 8 is 0 or x minus 7 is 0. So x could be negative 8 and x could be positive 7. And those are my two answers to this equation. Notice that negative 8 and 7 are not one of our off-limits values. So both of these are good answers to this equation. We can also check our answers by plugging it back into the original equation and making sure that we get something that's true. Now, you may decide that you want to use your calculator when you do those checks, but you can always check your answers when you're solving an equation. Let's do another example. Here I have a nice complicated looking equation. I've got a rational expression plus another rational expression equals something. My first step is to find the least common denominator, which means that I'm going to need to factor. I'm going to fast forward through the factor process and show you what this looks like with all the denominators factored. I have a 1 over a plus 2 times a plus 1, a 1 over a minus 1, and a 2 over a plus 1, a minus 1. Now I need to find my least common denominator. In order to have this guy covered, I need an a plus 2 and an a plus 1. In order to get this guy, I also need an a minus 1. My last denominator is made up of an a plus 1 and an a minus 1. And I already have an a plus 1 and an a minus 1, so I don't need anything else in my least common denominator. Now that I have my least common denominator, my next step is to clear the fraction. This time I'm going to go ahead and show you how to build up each of these fractions to have the same denominator before we clear the fractions. So I'll start with 1 over a plus 2, a plus 1. My goal denominator over here is a plus 2, a plus 1, and a minus 1. This guy is only missing the a minus 1 piece, so I multiply by a minus 1. But whatever you do to the bottom, you've got to do to the top. When I multiply straight across, I get 1 times a minus 1 is just a minus 1. So this guy can now be replaced with a minus 1 over a plus 2, a plus 1, a minus 1. Now we'll go ahead and build up my second fraction, 1 over a minus 1. My goal denominator over here is a plus 2, a plus 1, a minus 1. This guy has the a minus 1, but it doesn't have either of the other two pieces, so I'll need to multiply by a plus 2 and a plus 1, both top and bottom, which gives me my new numerator, a plus 2 times a plus 1. So there's my new second piece, a plus 2 times a plus 1, all over that least common denominator. Finally, we'll do the same thing for my third fraction. I have a 2 over a plus 1 times a minus 1. My goal is to get a denominator of a plus 2 times a plus 1, a minus 1. This guy has everything except for the a plus 2 piece, so I multiply by a plus 2, top and bottom, and I get 2 times a plus 2 as my new numerator. So this equals 2 times a plus 2 all over that least common denominator. I'm getting a little bit scrunched for space here. Fortunately, we're just about to get rid of those denominators. Now that every single piece has the same denominator, I can multiply through by that least common denominator and clear them all out. That will leave me with a minus 1 plus a plus 2 times a plus 1 equals 2 times a plus 2. This equation should look a little bit better. So let's go ahead and start working on solving this guy. I have a minus 1, but here I have a plus 2 times a plus 1. I'll go ahead and FOIL that out. This is really just distributing. So now I have a squared plus a plus 2a plus 2, and I'll distribute that 2 as well, so equals 2a plus 4. Now I'm going to do everything I can to combine like terms and clean this up a little bit. On my left-hand side, I only have the 1a squared, and then it looks like I have 1, 2, 3, 4 a's, so plus 4a, and a minus 1 and a plus 2 for a plus 1. This equals 2a plus 4. Before I go any further, I'm just going to take a moment to look at the equation that I've ended up with, now that I've distributed everything and combined some like terms. I see that I have an a squared, so this is going to be some kind of a quadratic equation. The way that I solve a quadratic equation is to move everything over to one side to get it set equal to 0, and then factor. So that must be our next step. I'm going to go ahead and subtract 2a and also 4 from both sides, which leaves me with a squared plus 2a minus 3 equals 0. Now I've got a quadratic thing set equal to 0. I'm going to try factoring it. And this should factor as a plus 3 and a minus 1, which gives me two little equations. A plus 3 is 0, or a minus 1 is 0. And finally, a is negative 3, or a is positive 1. However, before I decide that I'm really done, I should go back and check my answers to make sure that they really work. This time, I'm going to show you how I put that into my calculator. Remember that this is our original equation, and these are the two answers that we'd like to check. To check and see if a equals negative 3 is a good solution, I'm going to start by plugging in negative 3 to each a on the left-hand side of the equation. Over here are the calculator keystrokes that I used to make sure that my calculator interpreted this correctly. Notice that I put the negative 3 in parentheses wherever there was an a, and I also put the whole entire denominator of my fraction in parentheses each time a denominator came up. Turns out I get 0.25, or 1/4, when I plug negative 3 into the left-hand side. Then I went ahead and plugged negative 3 into the right-hand side, and I also got 0.25. So negative 3 is definitely a good answer. However, when I go to plug in 1, my calculator spits back this error. Error, divide by 0. That means something went horribly, horribly wrong. Looking back at my original equation, I can actually pretty easily see what it is. If I plug a 1 in here, I'm going to have a 0 in the denominator, which is going to cause division by 0. Division by 0 is bad news. So a equals 1 is not really one of my answers. My only answer will be a equals negative 3. Now that you've seen a couple examples, it's your turn to try solving some of these rational equations. So here's the first one for you to try. Go ahead and pause the video, solve this equation, check your answer, and when you're ready to talk about it with me, go ahead and play the video up again. And we're back. Let me show you the steps that I took to solve this problem. My first step is always to find the least common denominator. This time my two denominators are already pretty factored, and my least common denominator is pretty easy to find since it's just x minus 3. It's also pretty easy to clear since both fractions already have the same denominator. I can essentially just set their two numerators equal. Now I have x plus 5 equals 2 times x plus 1. I distributed the 2, pushed some things around to get x equals 3. Now, that seems pretty good, but it's time to check my answer. And when I plug it back in, I end up with division by 0 on the bottom. So this tells me actually 3 is not a good answer, and I don't have any solutions to this equation. Before you go, I have one more problem for you to try and solve. So I'd like you to pause the video and then try solving this problem, check your solutions, and then we'll talk about it when you come back. And we're back. So let's look at this last problem together. My first step is to find a least common denominator, which means I'm going to need to factor all of these denominators. Fortunately, two of them are just single terms, so that's all right. My last denominator I factor as x minus 4, x minus 2. Now it's easier to see that my least common denominator is x minus 2, x minus 4. That covers all of my possible denominators. My second step is to clear the fractions. I decided to do this by multiplying every term by the least common denominator. That caused the x minus 2 to cancel here, leaving an x times x minus 4. On my second term, it caused the x minus 4 to cancel, leaving me with a 1 times x minus 2. And on the right-hand side of the equation, everything canceled, and I was just left with the 2 from the original numerator. My third step is to solve the resulting equation. The first thing I want to do is distribute everything so that I can see what sort of an equation this really is. I end up with x squared minus 4x plus x minus 2 equals 2. I do some combining of like terms, and now I have x squared minus 3x minus 2 equals 2. What I see here is that this is a quadratic equation, and the way that I solve quadratic equations is by setting them equal to 0 and then factoring. So I'll move this 2 over by subtracting 2 from both sides, leaving me with x squared minus 3x minus 4 equals 0. That factors nicely as x minus 4, x plus 1. Now I take each factor, set it equal to 0, and that gives me x equals 4 and x equals negative 1 as my answers. I'm not quite done yet though. My last step is to check my answers, and I found that when I plugged in 4, I got some division by 0. However, negative 1 was just fine, so I crossed 4 off my list of possible answers, and x minus equals negative 1 is my final answer. That wraps it up for section 6.5. Happy studying, and I'll see you in class.